What would happen if you accidentally wiped the config of your Cisco switch? That's exactly what happened to me while building my enterprise home lab. And surprisingly, rebuilding the configuration wasn't the only part of the problem. There were a couple of layer 1 and layer 2 issues that could have easily been mistaken for routing problems. And I'm going to break all of that down for you in this video and more. And this video is going to kick off a series of what I call 30 days, 30 tickets, where every day I work at least one ticket, like a Cisco CCNA associate, which I am. And I'm just going to break down the whole process for you and take you along for the ride. So let's get into it. Let's take a look quickly at the layer 1 stuff. So here's my literal home lab, what I have configured so far anyway. I have my Cisco 2911, Cisco 3550, my ASA, and my Dell PowerEdge down there. Currently working on setting up the ASA. We'll make another video about that. PowerEdge server is currently connected to the switch. We've got the switch and the router, which is mainly the switch, what this video is going to be about. But we have basic router on a stick configured between these two, trunking on port FA01 to G00 of the router, and access ports configured for basically for the rest. But internet port is FA014, goes to the switch, which another switch which connects to the internet modem, and 12 goes to the server, and 8 is just kind of a test port. 10 also goes to the server, and 8 is just kind of a test port that I'm using right now. I have this configured for DHCP. Currently, port 8, I'm able to plug that in and get a DHCP address in. So yeah, so that's the basic layer 1 stuff. Don't spend too much time talking about that because I'm going to talk more about the config in a presentation that I have here for you. So let's get into that.
Presentation documents the restored and clean baseline configuration of my Cisco 3550 switch. The goal was to rebuild the switch after a wipe, restore DHCP and routing functionality, and create a clean, scalable VLAN architecture for my home lab. Here's the topology diagram that I made. It's pretty rough, but you get the idea. Right now, it's pretty basic. I have plans to expand beyond what I have here in this diagram, but just to help you visualize, I also obviously showed you the physical equipment already, but let's take a look at this diagram quickly. So we have the internet source here, the ISP modem, which connects to a little TCP uplink switch on port 14, which connects to port FA014 of my Cisco 3550 switch. So that's my WAN uplink, my internet access switch. Then I have my switch connecting to my router on port FA01 to port G00 of my Cisco switch here. So that's the trunk port. That's the one that carries the 8021Q trunk link between the switch and the router. Then on port 12, FA012 I believe it is, I have my Dell server here. And I'm of course working on getting my ASA configured, so my ASA is technically connected as well. So next, let's look at what happens when a core switch goes down and why it's considered a major outage. So enterprise is losing a core switch's configuration is a major outage. Users drop, servers go offline, management access disappears, the routing breaks. And so in my home lab, when I wiped my 3550, it did exactly that. So routing breaks because, like I was explaining with that router on a stick, if that trunk link's not there, and if it doesn't have the switch sort of segmenting traffic, telling the router, send this here on this VLAN or that VLAN, router on a stick doesn't work, and DHCP can't work. So that's what happens. So internet becomes effectively useless. So imagine if you're a business, everything's on the internet nowadays, but especially imagine if you're like a retail company or something and you have a register where you can't make any sales. So you lose a lot of money per hour or possibly per minute for every hour or minute that it's down. So that's why it's considered a critical, this would be considered a critical ticket. So the goal is to restore the network quickly, cleanly, and with proper documentation, as I have. So how we built the lab. Again, much like the diagram, my home lab is built to mirror a small enterprise network. So the 3550 sits at the center of everything, and so when it went down, everything went down. But I have the switch, the Dell PowerEdge R730. I'm going to have a wireless LAN controller. This is my plan to expand. Obviously, the ISP modem. I have my Cisco 2911 router currently configured for router on a stick. My Cisco ASA firewall for a future DMZ, working on configuring that, and my Raspberry Pi for VPN, Nginx, and monitoring. Next, to rebuild the switch cleanly, I followed the same workflow I'd use in a real consulting engagement. So first, I recreated the VLAN architecture, defined the VLANs 10 through 95 in this case. I may or may not end up using all of those. That's a lot of VLANs, we'll see. And gave them clear names. Then I rebuilt the trunk to the router on port FA01 like I explained. Then I reassigned all access ports with the correct VLANs. Then I restored DHCP and routing, made sure that worked, pools, inter VLAN and NAT on the 2911. Then I validated the connectivity, and then I documented the process and technically identified opportunities for automation. Before we dive into troubleshooting, let's quickly talk about VLANs. A VLAN, or virtual local area network, allows a single physical switch to behave like multiple logical switches. Even though every device is connected to the same piece of hardware, devices in different VLANs are separated into different Layer 2 broadcast domains. For example, this PC belongs to VLAN 10, while this PC belongs to VLAN 100. By default, they cannot communicate directly, even though they're plugged into the same switch. The trunk link carries traffic for multiple VLANs between the switch and the router. So this one might be something like sales, where they do a lot of talking on the phone and Zoom calls and stuff, and this one might be engineering, where it's a lot of pushing stuff up to GitHub and stuff. Voice traffic gets prioritized, so you wouldn't want that to be on the same VLAN as engineering, because they'd collide, they'd interfere, and the quality would drop. So think of a VLAN like a virtual port. Now the question becomes, if VLAN 10 and VLAN 100 are isolated, how do they communicate? That's where router on a stick comes in. So this is the trunk link here, FA08, like we discussed. That's where you allow the VLANs. And it's this single link is configured as an 802.1q trunk link. It carries traffic for multiple VLANs simultaneously. Now G00.10, that's the logical interface for VLAN 10. Again, that's the sub interface. It's a logical interface. And it becomes the default gateway for VLAN 10, like an IP address for VLAN 10. Same thing for G00.100. It becomes the default gateway for VLAN 100. Then when a computer in VLAN 10 needs to reach VLAN 100, it sends the packet to its default gateway. The router receives tagged traffic on the appropriate subinterface, routes it, and then sends it back towards its destination VLAN. So that's how these two PCs could communicate in different VLANs. It's like the router kind of intercedes on their behalf. We identified opportunities for automation. So the point of the rebuild was not about creating the final enterprise network. It was about restoring functionality quickly and documenting a clean baseline that supports future growth, like I explained in my plan for expansion. Rebuild, segment the network, route between VLANs and the internet, verify connectivity and harden access. These VLANs represent the full logical segmentation of my home lab. Only VLANs 10, 20, 30, and 70 are really active today for the most part, but the others are predefined for clear future expansion. In this design, I've reserved a dedicated management VLAN for infrastructure devices during the initial rebuild of the lab. I temporarily use VLAN 10 as my management network while I restore DHCP and core connectivity. As I continue building the lab, I'll migrate management services into their own dedicated VLAN, and you can see what those VLANs are here in the table below, and the flow of traffic between them here in this visual. So rebuilding the switch for a clean baseline here. So this is kind of a sample config here. It's not 100% indicative of how my switch is configured, but you get, this is to give you a visual to give you a general idea. But here, how you would rebuild a switch from scratch. Erase and reload, set identity, build the VLAN, assign access ports, save the config. Kind of like I explained already, that's how you do it. The diagrams and configuration snippets in this presentation are simplified examples to illustrate the architecture and design concepts. The Live Lab configuration has evolved as I've rebuilt and expanded the network. So some details such as VLANs, management, addresses, and host names have been generalized or sanitized for clarity and security to the extent that that's necessary. But as you can see here, 802.1q trunk link, the physical link that carries the VLAN and frame tag with the VLAN ID, like I explained. Native VLAN, it should be it's not VLAN 999, but the idea is untagged traffic traverses this VLAN, an unused VLAN to blunt VLAN hopping. So anyway, then on the allowed list, you see 10, 20, 95. I have every VLAN should be allowed, for example, on the trunk port. So this, as you can see here, is really an actual config of an interface on my switch. Specifically the trunk link between the router and the switch. As you can see, you set the trunk mode, and then you set certain VLANs to be allowed on that trunk. You choose which VLANs can traverse that trunk link. That's how you configure router on a stick, starting with the switch. This kind of expands upon that. So you can see we have the sub interfaces configured on the router. 0.10, that's your sub interface. G0, whatever, 0.10, 0.20, whatever. That's how you configure it. Acts as the default gateway for each VLAN. Router encapsulation.1q says, okay, I can receive that VLAN from the switch. DHCP pools, each VLAN gets its own pool, handing out addresses in the gateway. We'll talk about that more in another video. And then NAT and PAT on a default route. PAT overload hides the lab behind the LAN IP, and a default route sends the rest out. So it takes the LAN IPs, the private IPs, and translates them into one public IP, basically, allowing you to traverse the public internet. And this is what it looks like when you confirm connectivity. So ping into the internet, verification. Ping to Google from your router or your switch or your end device, PC, whatever. Check these commands: show IP interface brief, show IP route, show VLAN brief, show IP NAT translations. So each show IP interface brief, it's going to show you all the IPs on every interface that you have on the router. And show IP route is going to show you all of the routes, basically all of the static routes that you have in the routing table. And then show VLAN brief is a VLAN table to show you which VLANs are configured on which ports. And then show IP NAT translations will show you which LAN IPs you're translating to what WAN IPs, basically. So when you check those, you'll know that everything's up and running properly when you're getting an IP address from your end devices. Now for securing management in the switch ports, we use SSH so to encrypt remote access on the VTY lines. Strong secrets, we hash them using MD5 encryption, I believe. And no clear text passwords. We encrypted any plain text passwords, service password encryption. Port security, we configured just for sticky MAC learning to limit each access port to known hosts. We shut down unused ports. To idle interfaces disable and parked in an unused VLAN. And timeouts and banners and switch port non-negotiate kills your DTP. So basic security configuration there, won't spend too much time on that. So the CCNA skills that I applied in this lab were really all of the above here. VLAN design, 8021Q trunking, inter VLAN routing, DHCP services, NAT/PAT, static and default routing, SSH and hardening, port security, iOS troubleshooting, and I think given what I've talked about so far, you can see how I applied those to the lab. So from white switch to a fully routed lab with live internet access. So let's talk about the key VLANs and their roles. VLAN 30 is the current working VLAN with DHCP. Really, that's the one that I've tested with. But anyway, VLAN 70 is the WAN uplink. VLAN 10 handles management. The rest are staged for future services. This port map reflects the actual working state of the switch today. Every port is labeled, documented, and is aligned with its VLAN. So like we talked about port 1 here, that's the trunk port. That one's connecting to the router on G00. Here we go. Here we have 2 through 7. Those are just kind of random access ports for future expansion. 8 and 10 go to my server. And 9 is another access port for future expansion, user port. 11, and then 12 is my management VLAN, and 14, as you can see, is my WAN. That's the one, my uplink that goes to my server. Those are the really important ones, but That's the general VLAN scheme. The trunk to the router carries all the VLANs. The router handles inter VLAN routing, DHCP, and NAT. And here is a little visual to help you see that a little more easily. So you can see the loud VLANs on the trunk here, 10 through 70. Those are allowed to traverse this trunk. And then the router subinterfaces, G00.10 management, so that corresponds with VLAN 10. As you can see, that pattern continues here. This is the clean, rebuilt configuration. It's stable, predictable, and easy to expand. So, host name, VLAN creation, trunk config, access port config, voice VLAN, port fast, no shutdown. That's the basic switch configuration. This is the core of the switch config, VLANs in the trunk. So, this is what it looks like when you type out the commands. So, for example, VLAN 10, name management, and then that kind of repeats. Then you pick the interface that you want that VLAN to be on, you give it a description, a name, then you pick the switch port mode that you want it to be on. In this case, we want trunk, because again, this is the one between the switch and the router. And then you pick which VLANs you want to traverse that trunk with the VLAN allowed command. These access ports match the physical layout of my home lab exactly. So the access ports are for the end user devices. So you can see those here. In this case, it's using VLAN 20, interface 20, or interfaces 2 through 7, 9, and 13 as an example, giving them an access port, and putting VLAN 20 on all of those. Anyway, so router side dependencies. The router is responsible for DHCP routing in that VLAN 30 is active in DHCP VLAN today. So VLAN G0 must be trunked. Subinterfaces must match VLAN IDs. DHCP for every active VLAN. NAT outside on VLAN 70 for NAT, for the WAN subinterface for the NAT boundary to the internet. NAT ACL, access to the control list, must include VLAN 30. We'll talk more about NATs and ACLs in a future video. Like I covered earlier, these commands verify the correctness of VLAN's trunks and port modes, these verification commands. So, as you can see, I explained them earlier. This shows you what you'd find on each command. So, VLAN brief will show you which VLANs exist and which ports are assigned. If you want a specific VLAN assigned to a specific port and it's not, that'll let you know. Interfaces trunk will show you what's trunking on what interface. So FA01 is trunking with all the right VLANs. Show interface FA01 will switch port will show you which switch port mode, and FA01 should be trunk. So then that's how you know you did it right. Show CDP neighbors will show you what equipment you're connected to. Show MAC address table will show you how what hosts are learned on what expected ports, and then show run pipe section whatever shows you the running config on that specific interface. This baseline sets the stage for a full enterprise-style home lab, as you can see, and as I've explained before. The next steps are the ASA firewall, building the DMZ, dedicated the ID rack, which is the server, potential plans for expanding storage, we'll see about that. 5 is voice, plus installing free PBX on a VM on my server. And 6 is a lab network for Cisco modeling labs. And 7 is for automation and backups. We'll talk more about a lot of this stuff in future videos. So this ticket really helped me reinforce a lot of good skills. Reminded me to keep backups. Reminded me to document everything and save off config somewhere. Word, GitHub, something. 3, label cables. 4, router on a stick is fragile. 5, clean baseline pays off. And 6, watch legacy service config. So where does this go next? Ansible planning is a future plan. Python configs and backups and scripts. Git version control. Auto topology diagrams. DHCP NAT templates. And config wipe alerts. And that concludes the switch, 3550 switch rebuild. Again, issues, the switch got wiped completely clean and everything was gone and down. The actions taken were we rebuilt the full VLAN architecture, restored FA01 trunk to the Cisco 2911, reassigned all access ports to match cabling, validated DHCP NAT and inter VLAN routing, documented baseline, port map, and rebuild guide. Outcome was the network was fully restored, baseline configuration established, environment ready for future expansion. The network is now completely operational, continuing with my 30 days of 30 tickets roadmap. And as you can see, I've documented this here like an actual ticket. And overall, thanks for watching. If you want to see more home labs, network engineering walkthroughs, or CCNA level projects, please subscribe or follow along. This is Cameron, and I'll see you in the next one.